Today, we will be looking at Chapter 8, Section 7, which revolves around finding the limit of indeterminate forms both algebraically and using L'Hopital's rule. In this lesson, you will learn how to recognize and identify limits that produce indeterminate forms, apply algebraic techniques to evaluate these limits, and apply L'Hopital's rule to evaluate these limits. We call certain forms indeterminate because they do not guarantee that a limit exists at that point. Likewise, these forms also do not indicate what the limit is, even if a limit could exist at that point. There are several indeterminate forms. These forms include the limit of 0 over 0, the limit of infinity over infinity, the limit of negative infinity over negative infinity, the limit of infinity over negative infinity, or the limit of negative infinity over infinity. Two functions whose limit cannot be determined from the limits of the given individual functions often lead to these indeterminate forms. For example, if we take the limit as x approaches 0 of x squared over 3x and evaluate the limit as is, we will get the indeterminate form of 0 over 0. However, it is important to keep in mind that limits do not have to approach 0, infinity, or negative infinity in order for it to reach an indeterminate form. For example, if we take the limit as x approaches 2 of x squared minus 4 all over 3x minus 6, we will also get the indeterminate form of 0 over 0. When you encounter an indeterminate form, you can deal with these situations algebraically. For example, if we take the limit as x approaches negative 1 of 2x squared minus 2 all over x plus 1 and solve the limit as is, we will get 2 times the negative 1 squared minus 2 all over negative 1 plus 1, giving us the indeterminate form of 0 over 0. We can deal with this algebraically by first factoring out a 2 out of the numerator, giving us 2 times the quantity of x squared minus 1 all over x plus 1. We can then factor out the perfect square, giving us 2 times x minus 1 times x plus 1 all over x plus 1. We can cancel out the x plus 1 in both the numerator and the denominator, since they're the same factor, leaving us with the limit as x approaches negative 1 of 2 times x minus 1. And when we evaluate this limit, we are given negative 4. The same can be said with the limit as x approaches infinity of 3x squared minus 1 over 2x squared plus 1. If we evaluate the limit as is, we are left with 3 times infinity squared minus 1 all over 2 times infinity squared plus 1. Since infinity squared is just a larger infinity, we are relatively left with infinity over infinity, another indeterminate form. We can solve this indeterminate form algebraically by dividing every component of the original limit by x squared. This will give us 3x squared over x squared minus 1 over x squared, all over 2x squared over x squared plus 1 over x squared. When we simplify this limit, we are given the limit as x approaches infinity of 3 minus the quantity of 1 over x squared, all over 2 plus the quantity of 1 over x squared. And if we evaluate this limit, we are left with 3 halves. Likewise, for this example, we could also emphasize the 3x squared and the 2x squared, since they are the x components with the highest value. They have the x component with the highest power. This, when we solve the ratio, will give us the same answer as above, which is 3 halves. Algebraic techniques can also be applied to the limits of transcendental functions. For example, if we take the limit as x approaches 0 of e to the 2x minus 1 all over e to the x minus 1, and evaluate the limit as is, we will get an indeterminate form of 0 over 0. So, to algebraically deal with this transcendental function, we will first factor the numerator, giving us the limit as x approaches 0 of e to the x plus 1 times e to the x minus 1, all over e to the x minus 1. Since e to the x minus 1 corresponds in both the numerator and denominator, we can cancel these out, leaving us with the limit as x approaches 0 of e to the x plus 1, which gives us an answer of 2. However, it is important to keep in mind that not all indeterminate forms can be evaluated by algebraic manipulation. This often occurs when you have a limit which has a mix of both transcendental functions and algebraic functions. For example, if we take the limit as x approaches 0 of e to the 2x minus 1 over x and evaluate the limit as is, we will get an indeterminate form of 0 over 0. However, if we try to algebraically simplify this expression, we will get the limit as x approaches 0 of e to the 2x over x minus 1 over x, which still gives us an indeterminate form of 0 over 0. We can deal with these indeterminate forms by using L'Hopital's rule. L'Hopital's rule is a theorem which essentially states that if f and g are functions that are differentiable on an open interval from a to b containing c, and we assume that g prime of x does not equal 0 for all x in that open interval from a to b, and if the limit of f of x over g of x as x approaches c produces the indeterminate forms of 0 over 0, infinity over infinity, negative infinity over infinity, infinity over negative infinity, or negative infinity over negative infinity, then the limit as x approaches c of f of x over g of x is equal to the limit as x approaches c of f prime of x over g prime of x. So as long as the limit of f of x over g of x as x approaches c produces any of the indeterminate forms as mentioned previously, then the limit of f as x approaches c of f of x over g of x will equal the limit as x approaches c of f prime of x over g prime of x. L'Hopital's rule can also be applied to one-sided limits with the same criteria, as long as the limit of f of x over g of x as x approaches c from either the right or the left produces the indeterminate form of 0 over 0, or any of the other indeterminate forms of infinity infinity or negative infinity or negative infinity, then the limit as x approaches c from the right of f of x over g of x is equal to the limit of x approaches c from the right of f prime of x or g prime of x. The same can be said from the left. So as the limit as x approaches c from the left of f of x over g of x is equal to the limit as x approaches c from the left of f prime of x over g prime of x, given that in both situations the limit does in fact exist. So in summary, L'Hopital's rule basically states that if the limit of x approaches c of f of x over g of x is equal to one of the indeterminate forms of 0 over 0, infinity over infinity, negative infinity over negative infinity, negative infinity over infinity, or infinity over negative infinity, then the limit as x approaches c of f prime of x over g prime of x, well, the limit as x approaches c of f prime of x over g prime of x, provided the limit exists, will be L'Hopital's rule. So, let's look at some examples. In this example, we are asked to evaluate the limit as x approaches 0 of e to the 2x minus 1 over x. If we were to evaluate the limit of is, we would get the limit as x approaches 0 of e to the 2x minus 1, which is equal to 0. And of the denominator, we would get the limit as x approaches 0 of x is also equal to 0, giving us the indeterminate form of 0 over 0. To deal with this, we will use L'Hopital's rule, taking the derivative of both the numerator and the denominator, leaving us with a 2e to the 2x in the numerator and a 1 in the denominator. So if we evaluate the limit as x approaches 0 of 2e to the 2x over 1, we are given a value of 2. Next, we are asked to evaluate the limit of x as x approaches infinity of natural log of x over x. If we evaluate the limits of is, we are given the indeterminate form of infinity over infinity. So, to deal with this, we will use L'Hopital's rule, taking the derivative of both the numerator and the denominator, leaving us with the limit as x approaches infinity of 1 over x, which is equal to 0. Here we have an example which states that the limit as x approaches 0 of x plus sine of x over x. If we evaluate the limit as is, we will be given an answer of 0 over 0, one of our indeterminate forms. So we will use L'Hopital's rule, giving us the limit as x approaches 0 of 1 plus cosine of x over 1, which, when simplified and evaluated, gives us an answer of 2. On the right, we have the limit as x approaches 0 of 2 minus 2 cosine of x, all over x. And if we evaluate the limit as is, we are given the indeterminate form of 0 over 0. Using L'Hopital's rule, we can evaluate this indeterminate form, giving us the limit as x approaches 0 of negative 2 sine x over 1, which is equal to 0. Finally, we will evaluate the limit as x approaches negative infinity of x squared all over e to the negative x. When we evaluate the limit as is, we are given the indeterminate form of negative infinity over infinity, which can be solved by using L'Hopital's rule, as we take the derivative of both the numerator and the denominator, giving us the limit as x approaches negative infinity of 2x all over negative e to the negative x. However, if we evaluate this limit, we will also see it will still give us the indeterminate form of negative infinity over negative infinity. So in this case, we will just have to use L'Hopital's rule one more time. So we will take the limit as x approaches negative infinity of 2x over negative e to the negative x and apply L'Hopital's rule, taking the derivative once again of both the numerator and the denominator. This will give us the limit as x approaches negative infinity of 2 over e to the negative x, which now when evaluated gives us a value of 0. Not the indeterminate form 0, just 0. So, now for homework, I would like you to use L'Hopital's rule only and complete page 511 in the textbook, number 6 and number 10. Good luck.